Hello, can you hear me?
Hello.
I can hear you. Hello, Jimmy.
Oh, oh, there's my camera.
Jimmy and
Try this camera.
yeah, we can see you.
Oh, okay. I guess that camera's not working. Let me go back to this one.
Okay, so we have all the members present here in the lab, and we also have the rocket,
Yay.
like mostly built rocket present in the lab. So we also have a presentation with us. So shall I begin with the presentation?
I'm fine, but I would like to say that I am honored to be here with you. You have a very fine team.
Yeah,
You're doing
same.
good work, and I'm just very happy to be with you here.
Thank you very much.
I'm going to stop my video to save bandwidth, but if you ever
Okay,
want to
fine.
see me, just let me know. You know what I look
Yeah,
like. Not real pretty.
sure. So can
There
you
we
just
go.
confirm you can see the screen?
Yes.
Yes, yes.
Okay, so I'll just start the slideshow. So yeah, so you
Oh,
already know us. So we are the IT Bombay rocket team. So we are
oh,
the official rocket
one.
team of the Indian Institute of Technology from India.
Yeah, let me
And
interrupt just a
this is
second.
our video review presentation. Yeah,
They would like this to be recorded. Are you recording this?
yeah. This meeting is being recorded.
Okay, good. Thank you.
Yeah. So yeah, I'll just give a formal overview of the team. So we are a student team from IIT Bombay, and we are dedicated towards high power rocketry, as I mentioned before. And we have a total of 51 members, varying from UGs, PGs, and PhDs, and from various departments and years of their study. And obviously, our aim is to bring together the people interested in rocket science, and we also want to enhance the culture of rocketry in our institute and in the country, since it's not that much developed in India as it is in the US. And we have also competed in the Spaceport America Cup 2023 last year with an overall rank of 66. And this year we are participating in the competition for the second time. Which also has the executives under them. So we'll move on to the next slide, having the introduction. So over to Stuti.
Yeah. So our rocket is named Agastya. Our rocket is named Agastya. Agastya, which literally means the one who moves mountains. Agastya is a high-powered solid propellant rocket. It's powered by an M-class aerotech motor, which is M2500C. It has different systems like variable drag mechanism. It has a reefing parachute, and it has a weather station as payload. It is currently more technologically advanced than previous years' design. Next slide, please.
Yes.
Yeah, so I will introduce you with the basic rocket design. Our rocket has a lift-off stability margin of around 1.47. I'm sorry. It has a CP at 7.0 feet and CG at 5.74 feet. It has three body tubes in total of length 7.71 feet. It has a 50 centimeter nose cone with a 15 centimeter shoulder. It has a functional payload of mass 4 kgs. It has two aluminium couplers. The avionics bay, it is made of nylon discs and a polypropylene plate. The variable drag system is made out of aluminium and the flaps are made out of nylon. The fins are shaped trapezoidal with a rectangular cross section. It has a boat tail of 11 centimeter and the stability margin, as I said earlier, is 1.47 at liftoff.
Yeah, moving ahead to the structure part of the rocket, we have all the components mentioned over here, such as nose cone, tube, coupler, bulkhead, of which the nose cone, tube, inner tube, and boat tail, we have manufactured them in-house in our lab uh, using glass fiber and the epoxy. All the dimensions are mentioned over here. They are also present in our PTR report. We have done a lot of theoretical tests to ensure that uh, the rocket does not fail under any shear or load condition during its flight. So moving on to the fins, we have made a trapezoidal fin set of 4 fins. Next slide, please. So we have made a trapezoidal fin set of 4 fins. We have made the fins in-house. The dimensions of all the components are mentioned over here. All these sides are mentioned over here, and they are in centimeters. So thickness is 0.013 feet, and the flutter velocity and divergent velocity we have obtained from the fin sim simulations. They are 1.5 times higher than the maximum velocity that rocket can our rocket can reach. So that we have taken care of. Next slide.
Yeah, so for recovery, we are using a single deployment parachute recovery system. It contains a 2.5 meter unreefed diameter of the parachute. The suspension lines and the vent diameter, the all the other dimensions are as listed below. The we are using black powder for ejection. We used we did a test launch 1 kilometer launch, and for that we had used 4 grams of black powder. The diagram, the image you can see here, it is a reefing mechanism we made used to unreef the parachute.
Okay, so next we have variable drag mechanism. We are introducing this for the first time. So this design So this design is inspired by the chuck of the lathe machine, where the flaps are opened by using a spiral ring, which we will rotate using the servo motor. For that, we are using DS 3225 servo motor. It has maximum torque of 25 in Newton meters. So uh, this will increase a rocket's drag coefficient from 0.5 to 0.7, and we will use this mechanism to decrease our apogee as and when needed by opening this mechanism. So next, moving on to avionics.
All right. So we're going to be talking about the avionics. So first off is the logic for all the asteroid avionics. So you can see our first state is when we are idling on the pad, the air brakes are force closed and the data logging is off. And we have telemetry at 1 hertz to the ground station. The next state is the boost phase. And the condition for triggering change to the boost phase is either you get your altitude greater than 10 meters for the previous 0.2 seconds, along with your acceleration also being greater than 3g for the last 0.2 seconds. Either that, or say if for some reason the IMU encounters some sort of failure, if your altitude goes above 100 meters for the last 0.2 seconds, that can also be used to trigger liftoff and go to the boost stage. During boost stage, the air brakes are also closed, as is regulated by the SA Cup rules. Data logging is now on, and the telemetry is increased to a rate of 10 hertz. So after the boost phase ends, comes the coasting phase. The trigger for that is either you have 7 seconds from after liftoff, which is a decent bit more than the motor's burn time, or if acceleration is negative. So if when you are during boost phase, the acceleration is positive. So due to drag, the acceleration will be negative for 0.2 seconds. And after that, the acceleration should start increasing again. So that means your drag is eventually decreasing.
So if this condition or if 7 seconds from liftoff is met, then we go into the coasting phase. Now, only during the coasting phase, the air brakes are active and the rest is the same. So now there's a 10-second lockout for apogee detection as a safety measure. After that, once 10 seconds have passed from liftoff, you can either have negative vertical velocity for 0.2 seconds, or you can have 30 seconds after liftoff. Either of these conditions would fire the drogue fire. After that is done, we are descending under drogue. Air brakes are closed again. So when your altitude goes below 400 meters, dereefing happens. And of course, it has to be at least 5 seconds from drogue deployment. This is just a safety measure in case the pyro being fired causes some adverse pressure changes, which would change the barometric altitude. So after debriefing, it's pretty much the same. You just wait until touchdown. Touchdown is when at least 30 seconds from debriefing. So the rocket should have at least that much time, once again, as a safety measure for the pressure issue, as mentioned before. Altitude should be less than 50 meters, and the vertical velocity should be very small for at least 5 seconds. It's not written here because we didn't want to make it too small. And then it's just touchdown, telemetry is slowed down again, and data log is turned off the same amount. That was basic flow of the avionics logic. So next slide. So this is all the wiring schematics and powering for avionics. So we have a few boards. We have the Quartz GPS, which is the weight module used for tracking, and a Quartz altimeter as well, which is the altimeter Easy Mini. As on the SRAD side, we have our main board, a motor controller board, and a reefing board. Arnav will tell you more about these boards later. So for now, the GPS module is powered on when the avionics base is assembled. It has more than enough battery for to last throughout the whole launch. Same with the reefing board. Now the Quartz altimeter, SRAD main board, and motor controller are powered on using a switch on the launch pad once the rocket is raised upright. Of course, there's arming switches for all the pyros. So the Easy Mini only requires one arming switch. And we have one arming switch for the SRAD main board as well on both the pyros. The main board communicates with the motor controller via I2C to give it all the data necessary for air brake actuation. And right, so both the Quartz and SRAD boards can open the broke chute using this Quartz apogee pyro charge and the SRAD apogee pyro charge. Now, the reefing board will be packed inside the parachute bag, so obviously it's hard to arm that using a wired switch. So it will be turned on and it will be armed wirelessly by the main board once we have assembled the whole rocket and the main board is turned on. So it cannot accidentally fire the pyro before that. So once it's armed, and then all the reefing board, main board, or the Quartz board all three can fire this reefing E-match, which can dereef the parachute. And that's about it for the wiring schematic. No lithium polymer batteries for any of the SRAD boards as per the regulations. Only lithium ion cylindrical package cells. I'll hand it over to Arnav.
So this is the main SRAD board that you've created. It mainly runs on a Raspberry Pi Pico and RP2040. It's equipped with an accelerometer, an IMU, which is an BNO055. It's equipped with a barometer, which is a BMP 280. And other than that, it also has a pitot tube to measure the velocity of the rocket. It has an XB module right here for telemetry that is connected to an antenna which will be placed on the avionics board. Here, as you can see, would be our pyro mechanism. And so will it be here. This will be for the main parachute and this will be for the reefing parachute. And other than that, yes, we'll come to the reefing board later on, but this is just an extra security measure that we've taken to include the reefing mechanism even into the main board. Yeah. This will be the reefing board. This will be mainly near the parachute of the rocket, and it will be mainly handling the reefing board, a barometer here, and an MPU right here. We'll be arming a switch here, and based on which the reefing would take place. This will be the motor controller board. The motor controller board is mainly for the VDM. It will communicate using I2C to the main board because we haven't put a BMP. Yeah, because we haven't put a BMP or an MPU on the motor controller board due to its space constraints. So it will be communicating using I2C. At the same time, we even have a serial communication port, but we aren't using it for this iteration of the rocket. And you can see on the right side of the board. Yeah, that's it for the motor controller board. For the payload, this is the first time we are actually having a functional payload. So we are going with a weather station. So the weather station will measure these quantities as mentioned. It will measure the light intensity as we go up, the UV radiation, the air pollution, the humidity, temperature, and the air pressure as we go up. For the same, we have made another board, SRAD, which will be in the payload compartment of the rocket. This has all the priorly mentioned components right here on the board. And this will be powered by LiPo 2S, whereas the motor controller board will be powered by LiPo 2S. The reefing and the main board will be powered by LiPo 1S. Sorry, lithium ion, not a LiPo because, yeah, a lithium ion, my bad. And yeah.
Yeah. As far as testing goes, we have done a fair amount of testing. First of all, was parachute testing. So we wanted to get a good estimate of how much drag a parachute was actually generating compared to theoretical estimates. So we had get this in the PTR as well. So we hooked up the parachute to the back of the bicycle, and yeah, to the back of the bicycle, and we had a load cell connected to it, so we could measure how much force, how much drag the parachute was generating. We had a GPS chip on board the cycle as well, so we could measure its speed, so that the force and speed would calculate the coefficient of drag. We did 4 test runs, 2 of which didn't give very good data because I guess the GPS quality was bad because there was lots of buildings and tree cover in the campus. So yeah, we got a CD of about 1.2. Right, so you can see here from, yeah, they both converge to about 1.2. All right, so now for the for air brake actuation, we made a NAV filter as well, which was basically a common filter, which we could use to smoothen out the data because we couldn't actuate the air brakes in noisy data. That would lead to a lot of fluctuation in our estimated RPG. So you can see it was tested here initially in a car using GPS and IMU, and you can see it appropriately weighted the measurements. We could get a fairly smooth estimate first day. The SRAT telemetry, which we mentioned earlier, was an XB, was tested in campus across this range, which you could see is 1 kilometer. And yeah, the results were satisfactory. It worked great in the our subscale launch as well. So we are confident in our current setup. Over to propulsion now. Yep. Yep.
So the meeting is being recorded by one of our members through an external software. So I'll just, for redundancy, I'll start it here as well.
Recording in progress.
So we can now continue. Okay, propulsion.
Yeah, hi. So this is Karthik here from Subsystem Engineering Propulsion. So from our side, this year we'll be again going with the Aerotech M2500T motor for our rocket, and this motor will be requiring a RMS 9810 to 40 motor hardware, which will be given to us by our FOR gym. And the Aerotech M2500T motor we have already pre-approved from Aerotech, and we are going with this motor since it is a tried and tested one, and we have successfully launched with this motor on our previous uh, journey as well. So in the next slide, you'll see the design specifications. Next slide. So yeah, and also I'd like to add that we have some backup like redundancies as well, in the sense that we have centerings between our inner tube and our outer tube, and there is a clearance of about 1.5 between our inner tube and the motor. So all this will ensure there is no wobbling and appropriate thrust is achieved. And going to the next slide.
Yeah, so for the 1 kilometer
Yeah, over to
test,
Aditya.
for the 1 kilometer test that we had conducted using our SRAD motor, we used the propellant composition of KNSP with some added aluminium. This composition was arrived at by using NASA CA as a basis and then conducting a Crawford bomb test and further static motor fire tests. We for the motor we use two grains with a core diameter of 1.18 inch and 1.38 inch, and the total weight of the propellant was around 2.86 pounds. Um, Next slides, please. Yeah, so for the actual like 1 kilometer test, the motor was able to generate enough thrust to get the rocket up to a height of 3,385 feet. We were not able to determine the approximate thrust produced by the motor during the test because the accelerometer installed in the rocket uh, showed a reading of 16 Gs, which seems a bit excessive considering the size of the motor. Further details regarding the motor design have been mentioned in the following slide. So, should we go over that as well? Um, okay, I guess
Jimmy and Jim, do you want us to go over the details of the smaller subscale motor that we have built?
Jim Wilkerson here. I
Details.
don't need to see them. You guys have done great work, but if Jimmy is interested, please go ahead. Jimmy, what do you think?
Okay, I think I'm unmuted. Can you hear?
yeah.
Yeah, I
Yeah.
can hear you now.
Well, I'm fascinated by your motor work, but I think it's irrelevant to the task at hand, which is how your rocket's going to fly, how well it would adhere to the rules, and how well it's likely to actually fly. So I'd love to continue this conversation, but let's stay with the COTS motor for now.
Okay.
Okay.
Yeah.
So
So
the COS motor has been mentioned in the previous slides. So this is the COS motor that we are using, the Aerotech M2500.
Yeah. That should work very well.
Yeah.
Yes, we already booked this motor.
The mentor didn't blow up last year, so he's got a good confidence level that he won't blow up this year's either.
Good.
Yes, so if we are not to go into the details of the motor, so I think I can show you a small video of the launch. But
Yes.
okay, I'm sorry.
Okay.
Hello, can you hear me? Okay, so there seems to be an issue with Zoom, so it's asking me to upgrade to Pro for extending the meeting time. So,
Okay.
are you guys fine if I send you a fresh link right there?
Fresh link to rejoin.
Yes, because Zoom has a time limit of 40 minutes. I
Yes.
am really sorry,
Oh,
I
okay.
didn't take that into account.
Okay. So shall we back out and rejoin?
Yeah, I'll just send you a fresh link to join, and we'll be here
Okay.
right here.
So,
I'll be back shortly.
for you guys.
Hello.
Hello. Yeah.
Hey,
I'm
we're
sorry
back.
for that issue.
No worries.
Yeah.
I needed the break anyway.
Yeah. So we can move ahead. Okay. Yeah. So I guess that we did. Do you also want to see that, or do you want to move ahead?
The SRAM we don't need to see because it's not applicable to what we're talking about today.
Yeah. Sure. Okay. So we'll move ahead. So any specific questions that you may have?
Oh, my turn? Yes.
Yes.
I had some questions that relate to the two flow charts that were shown a little while ago, the one of the flight and one of the electronics. Can we go back to those and look at them?
Yes.
Or I could pull it up here
Yes,
and
we
share if
can.
that would work better for you.
Just give me a second.
Oh, okay. All righty.
No, it's fine. I'll just put it here.
Yeah.
I think you should be able to see the screen now. Yes.
Yep, there it is. Okay, let me get it where I can read it a little
Yep.
better. Oops, hang on just a second. That doesn't work well at all.
How do you zoom this? Yeah. Okay, we'll open the PTR instead. Yeah, that's easier to zoom into and stuff. You should be able to see the screen again.
Okay, coming through pretty
Yeah.
good.
No.
Recording in progress.
All right. So should I repeat everything?
Yeah, because I couldn't quite read the screen the first time through. So this helps a lot. So you're idle on the pad. Okay.
Yeah. Sorry about that. All right. So
Looks
this is the first stages when we're idling on the pad. They're
Okay.
closed, and we have right. Yeah, the transition from idling to boost is triggered when one of these two conditions is met. So the first
Okay.
one is if your altitude is more than 10 meters for the previous 0.2 seconds, 0.2 seconds.
Okay, good.
So either that, or if your altitude goes up 100 meters, that's also fine. Either of those can trigger the transition
Okay.
to the boost.
And this simply starts your data recording, right?
After boost comes coasting. Now telemetry a bit faster. That's about it.
Okay.
Okay, so now the air brakes are still closed during boost.
Okay.
The transition to coasting happens when either the 7 seconds have passed from liftoff, which is a decent bit more than the motor's burn time. I think 2 or 3 seconds more. And so it's that, or if you have negative acceleration for the last 0.2 seconds, and your acceleration is then increasing. So that means your drag is decreasing. So that would suggest that the motor has burned off. So if either one of those is met, then we are now coasting.
Okay.
Now,
Let me ask a
the air
second.
brake.
While we're on this, I see
Yeah.
seconds from lift out off force burnout detection.
Yes.
First time I thought you meant that it was actually sensing burn off at that point.
No, that's so if the other condition fails for whatever reason,
Okay.
it will force burnout detection after 7 seconds.
Okay. You're going to get a little bit of
Yeah.
leeway because your burnout will have happened in about 4 seconds. Okay, good.
So for the coasting phase, the only difference now is that the air brakes are now active and can be actuated to try and reach the target apogee.
Okay.
So the next stage would obviously be the ejection of the parachute. So now there's a 10-second lockout from the parachute negative for the past 0.2 seconds.
Okay, some of that got garbled.
Or if there's been 30 seconds from after liftoff.
Okay. Can I ask what is meant by drogue lockout? I'm going to stop video to get a little better sound here. Okay.
So,
In fact, I'll put it in chat.
Recording stopped.
Oops.
Recording in progress.
Roto, can you hear us?
I can.
Back. Jimmy, can you hear us? Yeah, we can hear you. All right, yes. Some internet issues. Yes, so at least so the parachute cannot be deployed. That is what this lockout is. Can you guys hear me?
Yeah, unfortunately, your video has got cut out quite a bit. Can you explain the lockout again, please?
Can you guys hear me right now?
Okay, I hear you now.
Right, so if you can hear me, so the lockout is the minimum time which must happen from liftoff for the parachute to be ejected. The parachute cannot be ejected before this time.
Okay.
It's a forced condition in the code. So the parachute cannot be ejected for 10 seconds after liftoff. That's a safety condition we've put there.
Okay, good. Got that. Looking at the next panel.
All right.
It says 30 seconds from
Yeah,
liftoff. Force drogue ejection.
Yes, that will force the parachute to be ejected.
So
because
30 seconds from liftoff, your parachute's going to be ejected regardless of the reading, the altitude reading. Is that correct?
Yes, because that is correct. I think that's because that's more than our simulated flight time with some safety margin as well.
So that's your backup.
That's our backup. Absolutely.
Yeah. Okay. Got it. Good.
It's either that or negative velocity, which means apogee has been reached.
I see. Good.
So after the chute is deployed, so we have descent under the chute. Air brakes will be closed after this point. Just no use for them. So now for dereefing the parachute, the altitude has to be less than 400 meters. And now the ejection of the chute might cause some adverse air pressure changes.
Right.
Which might throw off our barometer, which is measuring our altitude. So we just put a 5-second lockout for that as well after shoot. So that doesn't accidentally somehow disreef the parachute.
Okay. All right.
Is that fine?
Let me back up just a step.
All right.
Your descent
So
under
once
drogue.
the parachute has been disreefed, now it's just descending until we touch down.
Okay. Okay, I've got it. So you're saying at least 5 seconds from drone deployment and the altitude
Yeah.
less than 400
So
meters. So, okay,
descent
got
under
that.
drogue, it's just air brakes are closed. Data logging is
Okay.
yeah. So yeah, then the parachute is reefed, and then we 30 seconds even. The altitude has to be less than meters, and the vertical velocity has to be close to 0.
Okay.
And then that's it. Then we just detect touchdown. We turn off data logging, and yeah, then we just go recover the rocket.
Okay. Excellent. Thank you. Now that I understand it, it makes perfect sense.
Is that all right?
Yes. Can we see the next slide?
Would you like me to do the wiring schematic as well again?
What? No. What? I just have some specific questions
All right.
about what I'm seeing here. Let me adjust my view just a little bit. I can see more things at once. Oh yeah, can we go to the next page? Page 47. Okay, there we go.
Yep. This is page
Right.
47.
Yes, I have questions about the arming switches and the signal going to the reefing mechanism. I see you have arming switch 1 controlling or sending a signal. Actually, it looks like it's going to send the power to the E-match for the apogee charge. Okay, but it's going to send a
So
signal.
the E-matches, yeah, the apogee charge and the E-match are they're just electrically disconnected until that arming switch is shorted. They're not sending any signals. That's what the arming switch means here.
Okay, but the arming switch will be turned on at some point, right?
Right. Yes.
And that will allow the signal to go through when the time comes, right?
Yes.
Okay, so it's a single switch, but it uses 2 poles, a double pole switch.
Right. So in the COTS altimeter, there's just one screw terminal which you have to short to both these switches.
Okay, so you're shorting the ground or disconnecting the ground. Am I reading that correct? Oops.
Are you asking for the COTS or the SRAT board? Hello.
Okay, I
Can you hear me?
lost sound there for a moment. Can you hear me?
So are you asking for the COTS or the SRAT board?
Jimmy, he's asking, are you asking about the COTS altimeter or their designed SRAD altimeter?
Oh, I'm sorry. Right now I'm asking about the COTS altimeter. The one with arming switch 1. And just getting clarity that they're using a double pole switch, or are they disconnecting the ground to both devices?
Kuolo, we can't hear you. Your audio is cutting out very badly.
Me? Oh, okay.
No, Jimmy, I've got you. It's there. I know they're speaking because I hear little blips, but we're not hearing any of what they're saying.
Yeah. Tell you what.
So, in this sense, there's a 3.3 volt and a ground. And before we arm it, they are electrically disconnected. After we arm it, the connection is completed. And yeah, so basically that's what you're doing with arming. and after that, I signal you pass through it. So
Okay.
between the high, there's a there's a yeah. So between the high, there's this schematic of electrical things in the courts, and after that there's a ground. So we shot the electrical logic and the 3.3,
Okay.
and the same logic goes for SRAD as well. So in SRAD, for SRAD we're using a MOSFET, and it will be a 3.3, a MOSFET, and then the ground.
Okay.
And in the SRAD, to detect the arming, we have added an ADC. So the ADC can detect if the arming has been done or not.
Okay. Okay, I got almost none of that because it's coming to rather garbled. So what I think I'll do, well, I'll go ahead and tell you my questions if you're hearing me okay, and then we'll
Okay.
pick this up by email where we can be real clear about what's being said here, because this to me is critical. And there's some things here that might have difficulty passing the review at the spaceport once you get there. One is I only see one reefing mechanism here. I heard mention you were going to have two, but I only see one. Are you going to actually have two? Because I believe that'll be required. You need redundancy for everything.
Jimmy, I think they're not requiring the redundancy for the tender descender type reefing
Okay.
things. It's only one physical mechanism, but we can check that with Andy.
Okay.
So,
Make sure it applies to this one because it's not exactly a tender descender, but it is
Okay.
close.
Okay.
Hello.
Another question I
So
have.
for the SRAD, we have redundancy. We are not only using the COTS, we are using the main SRAD board and as well as the reefing board for it. Yeah.
Yeah, he's not talking about
And for
the
the main
electronics
particle
board.
detection, we are using
He's
the
talking about
COTS as well as the main board.
So each has
So
so
each
the
has
main
so the
parachute
main
has
parachute has two redundant has one has
two
two
options,
options
and the
and the
reefing
reefing has three options.
okay, but he's talking about there's only one physical reefing mechanism. Not there's two electronics boards. His question is there only one reefing mechanism and is that approved?
No, there are two.
No, there are two reefing mechanisms.
There are two reefing. Okay. Two same of what you showed us? The photo of the reefing mechanism?
Two same, yeah.
Okay, understood. Jimmy,
Okay,
did
good.
you hear that?
I got that. Thank you. That's just what I wanted to hear.
Okay.
But I have another question related to this, and that is how is the current going to get from your COTS altimeter to the reefing mechanism? Is it going through a wire?
Yeah, that's a
A wire.
Okay, so you'll have a long wire with a lot of kinks in it so it can stretch some, right?
yes.
Okay, good. All right, if we have time, I'd like you to actually show me that in the rocket or however you can lay it out if that's possible.
Jimmy, why don't we have them? Can we have them email you a photo of that laid out?
Yeah, if that might be better. Yes.
So, Colo, do you understand? Jimmy needs to see a photo of the reefing mechanism with the wires connected to the altimeter, as it would appear that the rocket was under drogue. So we'll need you to lay the rocket out so it appears that it is under drogue with the wiring mechanisms connected to the reefing part of the parachute. Does that make sense?
Yeah, that makes sense.
Yeah, we don't need you to do that now. We just need you to lay that out and then send us a photograph of that.
Sure, no problem.
Okay, good. Thank you.
What else, Jimmy?
Okay, I noticed that your stability at launch is listed as 1.47 calibers, which is just a hair lower than the minimum. But I noticed when you show your drawing and at other points, you show a much greater static margin there. So I imagine that 1.47 is a dynamic margin at some point in flight.
Yes. So basically, the
stability margin that has been mentioned in the slides of 1.47 is at the liftoff. So we can plot the stability margins from liftoff to the end of the flight on open rocket. So what we have mentioned is at the liftoff because it has been mentioned in the rules that it has to be 1.5.
Yeah, yeah. In my opinion, you could just round it off, but
Yeah,
it'd be
okay.
best if it could actually be 1.5 or higher. If you could put a tiny weight towards the nose or something. I don't know if that would do it. If it's dynamic, it may be more challenging to figure than just throwing a weight in the nose. But anyway,
So-
if you can
Yeah.
get that up to a 1.5.
So when
that-
we
that-
get when we get the motor assembled, we'll ensure that it's 1.5 before the rocket comes to the safe.
Okay. Good, good. I know that'd be really, really picky, but you want to meet the rules exactly on this in case somebody is a stickler for that.
Yes.
And we do have a couple of sticklers in the group.
And rightly so. In the right way, in the right way.
Right.
Okay.
What other questions?
I wrote down some things. What did I write down? One, as I see you seem to like the Raspberry Pi Co. Was that a yes?
Could you just repeat your question, Jimmy?
Oh, it was more of a statement. You seem to really like the Raspberry Pi Co. Is that working well for you?
Yeah, it's working. It's working really nicely. So
Yeah.
it runs in Python and it's very stable compared to an Arduino.
Yes. Let me see if I can turn on my video for a second. Okay, here you go. Here's something I'm building. It's an altimeter for model rocket to fly on an Alpha that uses a Pico attached with a very simple altimeter and accelerometer. That's the level of my sophistication. So I might be asking you questions about how you incorporate the Kalman filter because I need to do that. But that's another conversation.
Yeah, sure. Yeah.
Okay. Yeah. I think that's all the questions I had. Hard to read my notes, but you've done very well.
Okay, so in summary, the review is fairly you're fairly happy with the review, Jimmy, and I'm just summarizing. The one question we need to have answered is the physical layout of the wiring between the controlling altimeters and the reefing mechanisms.
Right.
Okay.
We'll get that done very soon.
Okay, so Colo, I think we can wrap this up then. And if you will take a photograph and email that layout to us, and then Jimmy will have a look at that and then make further comments if he needs to. Does that work?
Yes, it works.
Okay.
We'll do that.
Works for me.
Okay, I don't have any comments or questions either. So, Jimmy, if you don't have any more, Colo, if you don't have anything to ask us, we can wrap this up.
Indeed. Well, just once again, that I'm honored and delighted to be working with you. You're a great team. You're all good students, all good Rocketeers. I really look forward to seeing you in the desert in a little while.
Yes, thank you very much. It was nice to have you as our judge, Jimmy.
Well, thank you.
Yeah. Okay, thank you very much. I think
Okay.
we can end the meeting.
Thank you.
now.
We will see you next month and safe travels.
Yes, indeed.
Yes. Thank you very much, and we'll see you soon.
Bye-bye.
Bye-bye.
Thanks a lot,
Bye.
Jimmy.